Hello and good morning, everyone. Or good day. I should stick with my generic greeting. Hello, Olayeme. Hello, Saban. Hello, Francis. Hello, Ulvi. Hello, Danielle. Hello, Shagiz. Hello, Adolf. Hello, Collins. Hello, Seema. Some sun in Stuttgart today. Good. We had cold weather here where I am in Maryland, I think as well. The kind of northern part of the U.S. is experiencing unseasonably winter weather, and we're kind of on the outskirts of it. Hello, DeWitta. Hello, John. Let me begin here by kind of correcting one thing that I did yesterday. This is in the VC mini project. Hello to you too, Giannis. So in the VC mini project, right, we were talking about these methods for adding and subtracting, for example, right, and how we could define these methods. It was a little bit of bad practice, I guess, I did yesterday. Like in the add method, I said, well, if the other element in this binary operation is a point, I know what to do. If the other element is an int or a float, I know what to do. I said else I was returning a value error. Now, strictly speaking, what we should do, kind of good Python programming practice, so that these things, these point objects could work well with other objects or future objects, is we don't return a value error, we return this not implemented method, or this not implemented special value. And so instead of returning a value error, we're going to return not implemented. Because what this does, let's discuss things a little bit here again, just to describe what's going on. Like, suppose that the Python interpreter comes across this kind of expression, a plus b. Now, what does Python do? What does the interpreter do? It says, what is the type of this object A? And the Python interpreter, calls the method a dot double underscore add double underscore and b. Right, so this could be if a is an int, a float, a complex number, a list, a something, whatever the data type of this variable a, the interpreter calls the function, calls the method a dot double underscore add double underscore with b as the argument. If this method returns a result, then fine. The interpreter will take that as the value. if this returns this special not implemented, then it tries B double underscore the R add method and double underscore with A as the argument. Right, so this is what the interpreter is doing for us behind the scenes. So like the interpreter sees this expression A plus B, and it tries this method A. It looks at the data type of A. It says A dot double underscore add double underscore B. If this method returns some result, well, great. The interpreter takes that as the result of this addition. If this add method of A returns not implemented, then the interpreter tries, it uses the R add method on the object B. And similarly, well, if this returns a result, great. It will use that as the result of A plus B. This here might return not implemented. If this returns not implemented, well, then basically we get, like this kind of error message. So this is the better practice. This is the better practice than what I was doing yesterday of raising a value error. No, we want to return not implemented. This is the correct thing to do. And so I've gone through my definition of my class, and I've changed that to return not implemented. So, for example, right, with this class definition, well, we could define a couple points. The add method, right, we could use the add method, and our results, get what we then expect, this sort of mathematical definition of adding 2 points. Well, we add the first coordinates and add the second coordinates. Or subtracting 1 point from another, well, right, we will take the first component, subtract the first component, and then the second component, and subtract the second component, and we get this result. Again, if I take a point and I subtract a number, well, because we've given a definition to that operation, right, if the second argument is an int or a float, we know what to do. And we get this result. All right, there's a little bit of, weird rounding error because, well, we can't represent every floating point number exactly. Similarly, like the add method, well, this is, what I was saying here, right? We have a float and we add a point. Python looks at the float. So implement an add method to give a meaning to adding a float and a point. No, this add method from the float here will return not implemented. So then Python checks, does the point class implement an R add method to give a meaning to a point and a float? Yes, in this case it will return something. And so, right, as I'm saying here, this function call will correspond to using the R add method of the point class. This is because the float will return a not implemented in this case, and so the Python interpreter will go to the R add method of the point class. And well, since we've implemented an r_add method that gives a meaning when this argument is an int or a float, well, then we get a result. You know, if I try to add a string, well, this is when we get the not implemented method. And someone asked a question, how about for minus point of 10 and 1? Well, this is because the float class doesn't give returns not implemented. It tries the r_sub method for point, and we haven't implemented that. We could implement an r_sub method right here. Right, I could say, all right, I could implement an r_sub method. I could copy my sub method, let's call this r_sub. I don't need to have this bit here if the other instance is a point, because, well, if I'm going to r_sub, I know that the first element isn't a point. And we have to be careful here, you know, how we implement this. You know, we could try this out and check. Right? I mean, you know, if this makes sense, well, that might be another question. I could define an r_sub method like this. You know, so if I have a number minus a point, well, then I might interpret that first number, you know, right, as kind of a point that has two components that are equal to each other. You know, whether this is a good meaning or not. This will still be undefined. Right, as we said, the way we've defined now this r_sub method, so I'll take 4 minus 10, I'll get minus 6, and 4 minus 1, I'll get 3, and so, you know, we could give a meaning to this if we want to interpret this subtraction in this fashion. Right, so again, you know, we as the programmers have a power to do this. And yes, Shigiz, you're right. We don't have multiplication defined yet. That's coming in the next question. I don't have a definition if I take a point and multiply by 3 or 3 times a point. We haven't yet defined those methods. So, you know, we, as I said yesterday, you know, in principle, if I want to implement a new class all on my own, there could be a lot of work that I want to do, or a lot of work that I need to do, right? So we said the add and the sub methods allow us to use plus and minus operators. But I might need to define more than just add and sub. I need to define r_sub and r_add. How do you fix a problem when the denominator is 0? Well, you're probably going to have to throw an error in that case if in this rational class, right? So if, I mean, there's a little bit of a detour here, but in this Python notebook where we have this rational class, right, if the denominator is 0, well, you know, this doesn't make, you know, I can't make a sense of a rational, you know, when the denominator is 0, so yeah, right, I would likely raise an error. Right, I might do something like I could add some sort of error checking, maybe like in the init method, I could check is the denominator 0. If the denominator is 0 there, I might raise an error right then. You know, if again, you know, and if I'm trying to, you know, add in other operations, right? Things like add and div and mul and so on, right? At some point, if it's appropriate, well, then I might need to check, is the denominator 0? Right? And raise an error. For classes that I create myself, I might need to do this kind of error checking myself. To fix a problem when the denominator is 0, well, the only kind of fix to me at the moment that would make sense would be to actually raise an error. So, as I said, it might be, well, in the init method, I might add a check. Is this denominator equal to 0? If it is, well, raise an error. Raise a value error, for example. And, print out a message, oh, the denominator can't be 0. So that, again, that kind of error checking we might have to do ourselves. Let me shrink this down for a moment because I want to copy my class to use later. So I want to copy this, or I could copy this cell. That's probably the copy cell. Right, so with add and sub and probably ideally rsub and radd, right? If you define an add method and a sub method, you probably want to also go ahead and define an radd and an rsub method, so that then these operations, can be used in either direction. With the add and sub defined above, well, we can pass the question number 2 here. Again, so edit, paste cells above. I'm going to paste my class definition because I want to continue to add to this class definition. We want to give a meaning to multiplication. Right, there's scalar multiplication. There, as I said, there's different kinds of multiplication. We could think of vectors. There's a scalar multiplication, an inner product, cross products, depending upon which dimension, how many dimensions you're in. You might think of a matrix product, etc. We want to implement 2 kinds of multiplication. We want to implement scalar multiplication and inner product. So, both scalar multiplication and inner product, we're going to use the same, we're going to use the same operator, right? The mul method, as it says. This allows us to use the asterisk as a multiplication operator. So, as we were saying, right, we want to give a meaning to something like this. So, where we have a point and a number, or a scalar, or a point and another point, right? At the moment, this has no definition. And point 1 comma 2 times point minus 3 comma 3, this has no meaning either, but we can give this a meaning by giving a definition to the mul method, and similarly as before, right, perhaps to the rmul method, so that we could do some things in both orders. All right, so I'm going to come down here to the bottom. And I want to define a mul operation so that this will take both. So here, remember the idea. This method will be used if the first argument is a member of this point class. So I know that self is a member of the point class. I need to check what is the type of other. If other is a point, what am I going to do? Well, so a point times a point, I want to define this inner product. So what are we going to do? Well, we're going to take the x components and multiply the y components and add. So if I have 2 points, what do I want to return? I want to return self.x times other.x plus self.y times other.y. All right, take the x components and multiply, and take the y components and multiply and add, and this will return a number. So a point multiplied by another point, we're going to interpret this as the inner product, and we're going to return a number. If other is a int or a float, what am I going to do? Well, I want to return a new point. I'm going to take self.x times other and self.y times other. Let's add a bit of formatting in here. Right, this is going to return a new point. Right, so this is the other kind of multiplication we want to do. If I have a scalar, a number, an int or a float, and a point, I want to multiply the x and y components and return a new point. Otherwise, else, what am I going to do? I'm going to return this not implemented value. Now, I could also define an armol method, which we will do in a moment, right? But first, let's test this out. Let me, again, copy and paste. So, suppose I copy this cell. So, copy this cell. And paste this. Right, what happens if I print pt1 times pt2, and let's print pt1 times 4. Right, my add and subtract still work. My multiplication right here, well, if I have 2 points, so what are we doing? I'm multiplying 12 times minus 2 is minus 24. 10 times 3.5 is 35. Minus 24 plus 35 gives me 11. If I have a point times a number, well, right, 4, I'm multiplying 4 times 12, and 4 times 10, I get the point 4840. The isInstance method basically says, well, is this variable, what is the type of this variable equal to this type? Or in this case, is the type of this variable one of these two data types? So is instance question mark return whether an object is an instance of a class or of a subclass thereof. A tuple like x, with a tuple right here, may be given as a target to check this is equivalent to is an instance x of a, or is an instance of x of b, or so forth. Right? We're basically checking. So is instance pt1, pt1 of type point? Yes. Is instance pt1 of type int? No. This isn't of type int. It's not of type float either. Is instance 13 of type int? Yes. Is this of type float? Well, no. As ints and floats are different in Python. But I could check for, both. Well, and I'll get a true because, well, 13 is an int. Right, and this kind of thing is useful when I want to start implementing these kinds of methods, as you could see right here, right? I want to check, all right, I have a point, and I'm trying to combine it with something else. What is that other thing that I'm trying to combine it with? Is not implemented a keyword? Yes. The Python interpreter, will know what to do with this return not implemented. Ulvi makes a suggestion here. If I want to add an rmul method, there's a suggestion, well, let's return self.mul with other. And yeah, this is probably a pretty good also shortcut right here. So if I want 4 times pt1, right, by adding an rmul method, I'm going to be able to do expressions like 4 times pt2. And yeah, this might often be a shortcut which is used. I want to define an rmul method. Well, I will use the mul method which I've already defined. Because, the idea of the rmul method is, well, it kind of reverses the arguments. So the rmul, right, the idea is, well, the self here this is calling rmul on pt1. pt1 is coming in with as self, and the 4 then would come in with other. Well, we already know how to handle multiplication if the second argument is a float or an int. All right, and again, this will work for both floats and ints if I give my definition, correct. So yeah, this can often be a way to shorten your code in the case for something like this. You know, I could do something similar. I could do an R sub, but well, I might want to, negate things. I could. Do you have to define R mul considering that most likely interfloat will trigger? Well, right. The idea here is if I have an int or a float, well, we'll get an int or a float. We'll get an int or a float here. And, again, if I were to try to do a multiply print of a string times pt1, this is going to, this right here gives me the, the result from not implemented. Or similarly, the other way around, print pt1 times, a string. Can't multiply sequence by non-int. Oh, sorry, this first error triggers first. Let's comment this out. Oops. Apologies. Can't multiply sequence by non-int of type point. I mean, we could, maybe it might be slightly better in terms of getting an error message that if I explicitly, were to, I don't need this bit. In terms of the error message I get, it might be better, can't multiply sequence by non-int of type point. But, they'll have the same error message in a sense. Any questions about this? This should let us pass our grader, right? Because, this kind of thing, point times 2, well, the point times point will kick in first and get a int or float, and then we'll multiply the int or float by 2. And, something like, pt1 times pt2 times 2, right, as we said, Python will evaluate this first, get an int, or get a float in general, an int or a float, and then we'll multiply that int or float times 2. Because of the way we've defined R mul, and we've defined both mul and R mul, well, we could put the 2 wherever we want, right here. And we'll get the same result. So any questions on what I'm doing here, right? It's, again, my advice would be, well, if you define a mul method, well, you should also basically define an R mul method. Because, you would like to really be able to use these things in either order. Yeah, we're getting closer to question 5. Right, a distance, well, we want to compute a distance between 2 points. Well, paste cells above. Let's remove this. I'm gonna need to do this import. So I'm going to move this up here. Right, again, I'm copying my code from my point object, and I just want to keep on adding more functionality. Right, so once again, the point of defining both mul and rmul is so that we could use this point class as either argument if I'm doing this multiplication. If I don't define rmul, then 4 times a point will have no meaning. So the distance, well, the distance I'm not going to define as a double underscore method. There's no kind of double underscore method for, generally computing a distance between two things. So I'm just going to implement a method which def distance between self and other. Self and other. Because we've been doing it already, I'm going to say if is instance other and point. I'm going to return, what do I do here? Now I want the square root of self dot x minus other dot x squared plus self dot y minus other dot y squared. Else here I'm not going to return not implemented. Here I will raise a value error. Right, so what is my distance? Well, again, I take the difference in x components, square it, and the distance in the y components and square it, sum them, and take the square root to find the distance, right? This is the distance here. So again, well, I will redefine my point class. I need to redefine some points because, well, let's try 0, 0, and something I know what will be correct. 1, 1. pt1 dot distance pt2. I get the square root of 2. Right? 1 squared plus 1 squared is 2, and the distance here is the square root of 2. Right? Something easy, I know how to check. If I do pt3 is point something else easy to check, 0 and 3. Well, print pt1 dot distance to pt3. Well, my distance should be 3. Right, the point 0, 0 and the point 0, 3, well, the distance is 3 because the x coordinates are the same. So these just lie on the x-axis. And of course, well, I could be, sneaky, and I could stick in 2 times pt3. Well, then my distance becomes 6. 3 times pt2, well, I get 3 times the square root of 2. Right, so as I said, this is just a kind of regular method of this class now. So I access it by using the dot method, right? pt1 dot distance of something else. Of course, if I do pt1 dot distance to pt1, I better get 0. Right? A distance of a point to itself, I better get 0. And of course, you know, the way I define this, well, if I stick in a number here, well, then I get my value error. Right? It's not, you know, it wasn't necessary strictly right here to do this. You know, if I were to give something, you know, basically this other right here, it's looking for an x and a y attribute. If I had an object of some type that had, you know, an x and a y attribute and it wasn't a point, if I remove the is, you know, is instance, well, this would work. So any questions about this here? This should hopefully pass the grader, right? So our distance, it's the mathematical definition of distance. Here we want to do this clustering type of procedure. So let's just describe this a bit to make sure that everybody understands. So this is as I said, we want to solve a real world problem. We want to use our point objects, and we want to separate the points into groups of similar points. And we're going to have 2 clusters. So the idea, well, right, we're looking at the 2-dimensional plane. We're starting one point here at -1, 0, and the other point here at 1, 0. This is our starting points. Initialize one cluster at 1, 0, and one at -1, 0. What do we do? Well, we have a bunch of points. Assign each point to C1 or C2 based on whether the point is closer to the center of C1 or C2, right? And our centers start out at these 2 points. So, well, if I have a point here, well, this one's obviously closer to 1, 0 than it is to -1, 0. I'll put it into this cluster. You know, this point here, I'll put into this cluster. This point here, I'll put into this one. A point over here, I'll put into this cluster. And the idea is, you know, I do this for all my points. And, you know, when I've divided my points into these 2 clusters, well, we think I have one set here and I have another set here. What we do then, as we said, assign each point based on whether the point is closer to the center of C1 or C2, recalculate the center of C1 and C2 based on the contained points. Apologies, I meant to turn off my notifications. Right, so I want to recalculate the center of C1 and C2 based on the contained points. Well, basically, you know, maybe this point -1, 0 was actually one of the points in my set or not, I don't know, right? But what do? I basically recompute the kind of center of mass of these points. So I sum up the values of all the points, and I divide by the number of points, right? I basically can average the x components and the y components, and I get a new center, the center of mass of those points and the center of mass of those points. And then we repeat this process of, like, we kind of start over and we say, all right, now I want to reassign points to these clusters based on which point that it's closest to. And I keep on repeating this process until no points change from one cluster to another. Right? And then my centers of the clusters will have stabilized and my clusters will have stabilized. That's the idea of this clustering algorithm. Right? The algorithm will terminate when the assignments no longer change. So, we've defined all these points. Here we're going to create a cluster object. The idea here, well, the cluster, we're going to initialize it to be at some center. So like one of them is going to be at the center 1, 0, and one's going to be at the center -1, 0. So I need to, so this self points right here, I'm going to initialize to an empty list. The add point method is relatively easy. Well, I just do self.points.append. I'm going to add this point to this list of points that I'm storing right here. Right, so I want to do these kinds of operations. I have a new point. I want to know which distance here is smaller. And then, so I want to compute a distance from this point to this center and the distance of this point to this center. Whichever one of those is smaller, I'm going to add it to that cluster. If they're tied, I will have to figure out what I want to do when they're tied. I will arbitrarily choose to add it to the first one, whichever the first one happens to be. The update right here, the update step, is what we want to do right here in step 2. Recalculate the center of C1 and C2 based on the contained points. Well, right, I do this for each cluster independently. And what did I say we wanted to do? Well, we wanted to compute the center of mass of these points, right? I basically want to sum up the x coordinates and divide by the number of points that are here, and then I want to sum up the y components and divide by the number of points, and this will give me the center of mass of the collection of points. So how do I do that here? Well, I will define a sum. I'm going to sum my collection of points. And I think I need to kind of give a, well, this will, if self points is empty for some reason, well, this will give me a point object. This will give me the length of self.points as a list. I want to update the center of this cluster to be a new point, which will be, I take the x value, dot x, divide by this length, and the sum, the y value, and divide by the length. Right, I'm using underscores here because, well, these are both, sum is a method, and I just want, the actual point value. There's one other thing that I'm going to do in this update step, and this is to get prepared for the next step in this kind of iterative clustering algorithm. Right, so the idea is we've created a set of points. We, by doing some procedure, will define below by adding points, one at a time. When I'm done adding all the points, only then I'm going to call update. The update will recompute the center of mass of these points. The last thing I'm going to do is to reset my set of points to be empty. Right, so my cluster is, I have three methods. One which will initialize a cluster at a starting point. Thank you. I forgot a underscore on len here. Right, so my cluster, I will have a method to initialize a new cluster that's initially centered at some point. I create this empty set of points. I have a method which I can add a point to this list. And again, I have a method. The idea here is the update method I'll call after all points have been assigned to one cluster or the other. And this will compute the new center of this cluster of points. Again, we sum up the x coordinates, divide by the number of points, sum up the y coordinates, and sum up the y coordinates and divide by the number of points, and this will give us the new kind of center of mass of the clusters. And the last thing I'm going to do is I'm going to reset my set of points to be empty because I want to do this procedure again. Now, for this algorithm, well, we have a set of points. Here they're coming in as tuples. So these points right here are coming in as actually as a collection of tuples. So we're going to create points from these sets of tuples. We initialize one cluster starting at the point 1, 0, and one cluster starting at the point -1, 0. I'm going to keep track of, say, one of these sets of points. Right? I want to know, when does my clustering procedure end? Well, my clustering procedure ends when the set of points don't change. I'm going to iterate. So we pick a point, we compute the distance to the center of cluster A and the point to the distance to the center of cluster B. What do I do? Well, if the distance to A is smaller, what do? I'm going to, I say, add point to cluster A. Otherwise, I'm going to add this to cluster B. Right, so if the distance to the center of A is smaller, I put it in cluster A. Otherwise, I'm going to put it into cluster B. If the set of old points is equal to the set of points here, I'm done. Otherwise, I'm going to update the set of old points. Now, I have to be a little careful here. I can't just set A old equals A dot points, because then they'll point to the same list. And that's bad, because the update step right here is going to reset the list. So what I need to do, for example, is I need to create a new list of these points. All right, as I said, setting A old equal to A dot points is bad. It won't work, because then they'll point to the same list. And then the update step right here is going to reset this list to an empty list, and that's bad. Now, the last thing that I need to do, well, is I need to return the points of A and B. And we need to return them in the right order. The returned value should be the two centers of the clusters ordered by greatest X value. So, well, what do I want to do here? So, all right. Well, first of all, so let's suppose, right, I can have A dot center dot X, A dot center dot Y, and B dot center dot X and B dot center dot Y. This may or may not give them in the correct order. Right, this is a tuple. This is another tuple. If I sort tuples, well, they will sort by the first element of the tuple. I'm told I want things in order by greatest X component first. So normally, well, it would sort by smallest component. Well, if I do the reverse, I will sort by greatest component first. We could try this out, right? Compute points. Uh, 12 and 3 and 2 and -1 and 1. Compute result, sorry. Int and built-in, what am I doing here during the oh, I need to redefine my right, so, you know, as I said, we're out of time here. A couple things to keep in mind. I need to copy my list of points from my first cluster because I can't point it to the same list. Because the list gets destroyed during the update step. I need to make sure that I recompute my center of mass correctly. The tie breaking here, well, right, less than this. You might try less than or equal. Oh, I'm going to get the same results, probably. I mean, what you do with ties is, you know, up to you. Right, but as I said, one of the important things I think is to make a new copy of this list. Right, and you know, you could try this out. Of course, you know, if I have more points, well, my centers of mass are going to, you know, move about. The centers of my clusters are going to move about. Yeah, don't forget to reset this list right here to empty, you know, because otherwise you're going to have multiple copies of the same point. You divide the points, recompute the center, essentially remove the points, and then start over again. So I'm going to have to leave things there for today, as I have another lecture to give in like half an hour, or less than half an hour now at this point. So have a look at what I've done here, you know, see if it makes sense. Ask questions in the message board. I do look at the message board. And we'll see you on Monday. Some new videos will be made available tomorrow, and you'll get an email soon for, you know, new material. So I shall wish you all a great weekend, and we'll see you next week. This is the end of week 2 already. 2 weeks down. So have a good weekend, everyone, and we'll see you next week.